The last case that we look at in permutations, instead of arranging objects in a line, we're going to arrange them in a circle. So how does that change the problem? So what's the difference between placing an object in a line, placing it in a circle? So the difference comes down to how many ways you can place the first object. So if we've got a line, so just for the sake of this example, we've got 6 objects we're going to arrange in a line. Well, when I've got a line, there's a definite start and finish. There's the first spot, there's the last spot, and there's all the spots in the middle. I can name each particular one, and they're different. So I've got a choice of 6 different positions I can go in for the first object. But when it's a circle, I now can't name the spots. I'm in a circle, so which one is the first spot? Now you might say, oh, it's the top spot. And then I'll say, all right, rotate the circle 90 degrees. And now it's not the top spot anymore. So you can't define the positions. So when the first object comes along, it's only got one choice, and that's to go in the circle. Now, once the first object's in there, then I can define the other positions, because I can say, oh, okay, I've got one that's 1 to the left of the object that's in there, or 2 to the left, and so on. And so then it becomes like normal. So it's all to do with the first object. So line, number of arrangements, first object, n possibilities, as we saw. But in a circle, it's now just going to be one possibility. Put the object in the circle. Second object comes along. Now it's going to be the same. So it'll be n minus 1. Then n minus 2. And so on, all the way down to the last object, which of course has 1. So the difference between arranging in a line, there's our, as we're used to seeing, n factorial. But with a circle, we only end up with n minus 1 factorial. Or another way of thinking about it, n factorial was the number of ways that we arranged in a line divided by the number of ways we could arrange that first object, because now that doesn't matter. So n factorial divided by n, which again turns out to be n minus 1 factorial. So really all we have to remember is when we're placing objects in a circle, we just take one off. So let's look at some examples. So a meeting room, and as often you recall, when you go to meetings, often you sit around a table. So we've got 10 chairs around the table. Committee of 10 people includes 3 teenagers. How many arrangements are there where all 3 will sit together? So the number of ways we've got to organise the teenagers. The problem's still the same. Look after the condition first. The teenagers are going to be together. There's 3 of them, 3 factorial ways of arranging them. But now we're going to place our objects in a circle. Well, we no longer have 10 people. We've got a group of 3 teenagers plus another 7 people. 8 objects all up. But these 8 objects I'm not going to arrange in a line. I'm going to arrange in a circle. So I'll multiply by 7 factorial instead of 8 factorial. So 1 less. 30,240. We're going to hold an election for chairperson and secretary. What's the probability that they're seated directly opposite each other? Okay. Well, probability, so we know bottom of the fraction would be total number of possibilities, no restrictions. So 10 people in a circle will be 9 factorial, 1 less. So 9 factorial will go on the bottom of our fraction. Now, look after the condition. The president's going to sit down in the circle. Well, one choice, because at this stage no one's in the circle. So the first person to go sit in the circle's got one choice. They will then dictate the other positions. So they choose one way. Well, now the secretary's got to go and sit directly opposite. So the secretary's only got one choice. I have to sit opposite the president. And now the other 8 people are going to sit down. But it's no longer a circle. Because there are people in the circle, the positions are all defined, so it's just the same as a line. So it will be times 8 factorial for the other 8 people. So the probability will end up being 1 times 8 factorial on 9 factorial, which is 1 on 9. Which brings me to an interesting point with some of these questions. Sometimes logic is a lot quicker. Because think about this. President has sat down. There's 9 seats. Only one of those seats is opposite the president, therefore there's a 1 in 9 chance that the secretary sits opposite the president. So yes, sometimes simple logic can solve these questions a lot quicker. Let's have a look at an HSC one. 2002, a palindrome. You always got to like those. 7 people are to be seated around the table. First part, bit of a gift question. How many arrangements are possible? So no restrictions. Oh, okay, 7 people, but we're going around a table, so therefore we'll take off 1. So there'll be 6 factorial arrangements, 720. Second part of the question, 2 people, Kevin and Jill, refuse to sit next to each other. They're fighting at the moment. How many seating arrangements are then possible? It's often easier with this sort of question to work out the number of ways they are together and then subtract them from the total number of possibilities. So I'm going to work out how many ways they are. Well, put them together. 2 factorial ways they can be together. Group of 2 people, 2 factorial. They now become 1 object. So we are now going to seat not 7 people, but our group of 2 plus another 5. So 6 objects going around the table. So it'll be 1 less. So it'll be 5 factorial. 5 factorial. And that gives us a total of 240. Remember, we wanted the complementary idea. We didn't want the number of ways they are together. We want the number of ways they are not together. So 720 minus 240 gives me 480. It's just a little flow chart I've put in there, I suppose, a way of thinking about these sort of questions, where you go, okay, I've got a question. First of all, we've decided it is a permutation combination. Remember, permutation combinations is when it's without replacement. So if it's with replacement, we don't even start this flow diagram. We go, okay, I just got to go to the basic counting principle. So permutations, combinations. Now, do we have restrictions or not? We've got to sort that out. But the big decision we make is order important or unimportant? If order is not important, we're talking about a combination. If it's important, well, now the decision we make, we're arranging in a line, we're arranging in a circle. Circle be n minus 1 factorial, whereas a line would be n factorial. And then some of the other decisions, are we going to use all of them? That was just n factorial, you remember. Or are we going to use some of them? And that was npr. And then, when we were using all of them, we had another decision to make. Are all the objects different? Or are all the objects, I was going to say all the same. Now, are they all different or are some of them the same? And that pretty much breaks it down to all the different types of problems that we've looked at so far. 1995. Wow, 20 years ago now. But I really like this question. Okay, so we've got a security lock. 8 buttons, labelled A, B, C, D, E, F, G, H. And you get a 3-letter code to try and get in this door or whatever the lock's on. How many different codes are possible if the letters can be repeated and the order is important? So you could have a combination AAA, for instance. Well, because I'm reusing letters, it's not a permutation, it's not a combination. I use the basic counting idea. So it'll be 8 times 8 times 8, 512. Part 2. How many codes are possible if we can't repeat the letters, but the order is important? So we press the code, we go ABC, which would be different to the code BCA, which would be different to the code, and so on. So it's a permutation. So of the 8, I want 3 of them, 8P3, 336. Then the third one says, oh no, this is how the lock's going to operate. You've actually got to hold the 3 buttons down at the same time. So now it becomes a combination because the order doesn't matter because you've got to press them all 3 at once. So 8C3, 56 possibilities. So I like that question because it sort of went through all the different ideas with the same question. So 10i